So we're going to continue where we left off here. We just figured out that the derivative of e to the x is e to the x. And if we wanted to do chain rule with the derivative of e to the x, we would do the derivative of the exponent, which is the added part here. So we also learned that the derivative of 2 to the x was 2 to the x, ln of 2, that extra constant of proportionality. The derivative of any base, a to the power of x, would be you leave it the same and you do ln of the base. Now again, if this x was not an x but a function inside of a function like 2x or x squared, you'd have to remember to do the derivative of that exponent using chain rule. So let's do some examples here. It asks us to differentiate the function e to the tan x. When I look at this, I need to read it as e to some function. So this is chain rule here. So my derivative would be, you'll leave the function the same, times the derivative of the exponent, which the derivative of tan x is sec squared x. So that would be my derivative. Find the derivative of this function. So again, one thing we want to notice is that's not just x, so there's chain rule involved. That's not just x, so there's chain rule involved. And furthermore, there's product rule involved because I have a function, e function, times another function, the sine function. So we're going to go ahead and do product rule. So we do the derivative of e to the minus 4x, so we leave it the same. And derivative of the exponent is negative 4. So that's the derivative of the orange, times the other function, plus we leave the first function the same. And now we're ready to do the derivative of sine of 5x. So the derivative of sine is cosine of that argument times the derivative of the argument, 5x, would be 5. And then we would go ahead and simplify it. In this case, we can bring the constants out front, minus 4e to the minus 4x sine 5x, plus, and I can bring this 5 out to the front, 5e to the minus 4x cosine of 5x. And the nice thing when you have e's involved, you can factor out that e to the minus 4x. And sometimes there may be trig identities you can use to solve, but for now we're just going to leave it like this. And we just factor out the e to the minus 4x. So we're going to move on to the derivatives of logarithmic functions. For now, we're just going to go with the result of the derivative. So the derivative of ln of x is just 1 over x. And I could also prove that the derivative of log with some base b of x would be 1 over x, just like the ln function, but we have this added term here, which is ln of b. Now, I'm not going to prove either of these results. I have written the proof out here for you to look at, and it's also on one of the videos I've attached on Khan Academy for you to watch as well. Okay. My expectation for us is to be able to use these two highlighted formulas in our derivative rules. You may or may not get asked to prove this in the future, but for right now, the proof is there for your benefit. So I'll hold it here for a moment so you can look at it. Okay, so let's see how these two results are used. Oh, and there's that other formula I wrote down. They wrote it with the log being base A instead of base B, same result. So how do I do the derivative of this function? So we notice that it's a log function. We notice that the argument is not x, so there's going to be chain rule involved. I know my base is a 10. It doesn't have to be 10, it can be any base. So then therefore my derivative would be 1 over whatever my argument is, and my argument is 2 plus sine x. I'm going to add the ln of a term in there. So my ln of a would be ln of 10, which is my base. But now because there's chain rule involved, we need to do the derivative of the argument. So the derivative of 2 is 0. The derivative of sine x is cos x. and that would be our derivative. I can clean it up a little bit. Cosine x divided by 2 plus sine x times ln of 10. Okay, let's keep going. How do we differentiate ln of some argument? Again, this argument is not an x, so it's not x. So we need to do chain rule when we get to that part of it. So remember that the derivative of ln of x is just 1 over x, and then obviously the chain rule that needs to get implied. So here, y prime is 1 over, and I take the argument, which is x cubed plus 1. Now, but because that argument has chain rule involved, we would take the derivative of the inside, which would be 3x squared plus 0. And one last step to clean that up, 3x squared over x cubed plus 1. Okay. These two results down here are just confirming that when you have the inside of that argument that is not an x, you need to remember to apply chain rule for whatever that argument is. Okay, so here's some examples for us to try. The derivative of ln of sine x, 1 over sine x, 1 over x, or 1 over the argument, times the derivative of the inside. Derivative of sine x is cos x, so this result leaves us with cotangent x. Now here, again, we have a ln function. I'm going to rewrite this function to be ln x to the 1/2. So when I differentiate it, f of x, I get f prime of x, and now I'm doing chain rule. Ln is on the inside, so my outer function is the 1/2, so I'm going to do the power rule first. 1/2 ln x to the minus 1/2 times, now I'm ready to do the derivative of the inside, which is ln x, and the derivative of ln x is 1 over x. Okay. For now, I'm not going to simplify, but you would want to practice simplifying these expressions so that you can kind of clean it up, and we will be doing other stuff with these expressions later that you would need to know what the cleaned up version is. Now in this example, I'm asking you to do ln of this, and it looks like a lot of quotient rule, chain rule involved, but there's nothing saying that we can't just simplify this function before we move along. So what I'm going to do is I'm going to leave the derivative on the outside, but I'm actually going to use my log rules to simplify this. When I have ln of a quotient or log of a quotient, it turns into ln of the numerator subtract ln of the denominator, which you're going to see I'm going to write it as a power instead of a radical. And now this 1/2 is in the exponent, so that can come down. So I'm just simplifying the function, not even on the derivative yet. I bring the 1/2 ln x minus 2. And now that the function is cleaned up, I can take the derivative. Let's start with this first term. The derivative of ln is 1 over the argument. The derivative of the argument, 1, minus, there's a constant multiple. I'm going to leave the 1/2 on the outside. The derivative of ln of x minus 2 is 1 over the argument. There's my argument, times the derivative of the argument, which is 1. And I mean, I can clean up my function, not by much, and I could do more, but right now, again, we're just going to leave the function kind of in this form, just so we can pay attention to the new ideas of derivatives. Now, how would we deal with it if it was an absolute value of x? You could prove, which we're not going to do, but you could prove that when you're doing the derivative of absolute value of x, the derivative would be 1 over x, and you kind of drop the absolute value. So you have to pay attention here. The domain of absolute value of x is xer. The domain of ln of absolute value of x is that just x cannot equal 0. So when we end up taking the derivative, we want this x to represent the same domain as that function, which would be x cannot equal 0. So it says find f prime of x. The derivative here would just be 1 over x. You just drop the absolute value, and then the domain of this function works out to be identical to the domain of that function. Okay, this result, this theorem is telling us the same thing. If I don't have an x in the argument, but I have some other function, I need to make sure that I do the chain rule by multiplying by the derivative of the inside of that function when you get to that step. Okay, so let's go through these examples. Ln of a function, we go 1 over the function times the derivative of the inside, which is 2, simplifies to 1 over x. I do the derivative of ln of something. Derivative is 1 over the argument times the derivative of the argument, which is 2x. Just going to put that 2x on the numerator as a cleanup step to make it look more rational, which is the type of function that is. This time, when we look at this function, I have a ln x and I have an x. So this means I have to do product rule. The derivative of the first times the second plus, I leave the first function the same. The derivative of the second is ln of x. The derivative of ln of x is 1 over x. So now clean this up. The derivative is ln of x plus 1. Ln of x all cubed. I look at my outer function, so this is something to the power of 3. So when I do the derivative, I get 3 something to the power of 2. I've dealt with the outer part of the function, which is the cubic. And now I'm ready to differentiate the inner part of the function, which is ln of x. The derivative of ln of x is 1 over x. And I just clean up my result. We could write this like trig, where we put the squared inside the ln and the x if you would like to have simplified notation. But otherwise, you can just leave it as 3 ln x squared on the whole ln x divided by x. And we're done.